Okay, so I want to start this video by posing a problem. So a few things to start off with that we know about circuits. So we know that a power source is providing our electrons with electric potential energy, and we know the electrons then move around the circuit and this energy gets transformed into other forms, maybe heat, maybe light, maybe sound, whatever you like really. So we also know that different size resistances in series will transfer different quantities of energy. So a bigger resistor will cause an electron to transfer more energy. And we know this because we can measure it with a voltmeter. So we might measure the potential difference across one resistor is bigger than the potential difference across the other. And that means we've got this different amount of energy transfer. So a question that poses itself at this point is, how does an electron know how much energy to give a component? So why doesn't it give a component more energy or less energy? Like, how does it know how much it should be giving? Well, the simplistic answer to the question doesn't. Like, the electron is not a conscious being. It's not making a decision how much energy to transfer to different things. That's the first thing to address. In terms of actually getting a more helpful answer to the question, I want to draw an analogy to a different system that operates by very similar rules to the way a circuit works. So, on the system you can see on the left, what we've got is a speed-controlled motorway. So you'll see at the top here, each of the lanes is being maintained at 40 miles per hour. And the reason you do this is this speed optimizes the number of cars that can travel through a given point in a fixed period of time. And if you didn't have these speed restrictions, some people would be trying to go through at 90 miles an hour, some would be trying to go through at 30. We get all this massive range of speed, and that ends up being really inefficient at moving through. We end up with lots of traffic. By regulating the speed, we can actually optimize the number of cars we're getting through per second. And it's the same idea is going on with a circuit. Essentially, what the circuit is trying to do is optimize the number of electrons passing through a circuit, say per second or some unit of time. So then the question you might ask is, why? Like, why is our circuit trying to optimize that? Well, I think it's helpful to consider what's causing happen in a circuit in the first place. And the thing that's causing everything is the power supply. So I've chosen a cell here, but it could equally be a power pack. They're all doing the same thing, just in slightly different ways. So what your power source is doing is it's creating regions where electrons are close together and further apart. And it's doing that by moving electrons around. So you can see here, essentially, this cell is moving electrons from one side to another. We get a region of high electron density, so where electrons are closely packed together over here, and electrons are spread out over here. And that's why we have a high electric potential energy here, or a low electric potential energy there. So that's all fine, but why do we actually get this movement of electrons? Why do we want to optimize the number of electrons moving per second moving through our circuit? Well, the thing you need to remember is electrons have the same charge, and that means they're going to repel each other through the electric force. But if they're closer together on this side, that's going to have a stronger repulsive effect than this side over here. And what that means is there's going to be this repulsion is going to move electrons around a conducting pathway if we connect one side to another. They're not going to be able to move through the battery because in a cell there's a chemical reaction making electrons move across this way. So they're going to have to go around a conducting pathway on the outside. So that's why our system is trying to move electrons, and it's essentially trying to get rid of this electron density difference as quickly as possible. So that's why it's trying to optimize the number of electrons per second moving through a circuit. Okay. So a question you might want to ask at this point is, okay, that's fine, but what happens if there's not a conducting pathway? What if we just have two wires plugged into our cell? So that might look like this. So our power source will briefly be able to still move electrons, because it's still capable of taking electrons from one side and putting them to another. The question might be, well then, why does it stop doing that? And the reason is eventually the electrons will become so dense on this side the repulsive force from them will essentially stop the chemical reaction. The chemical reaction won't be able to do enough work to move any electrons across anymore. And we get stuck in this situation you can see here. We've got a high voltage side, we've got a low voltage side, but there's no mechanism to essentially get rid of that voltage difference, or potential difference if you like. Okay, so that's what's going on without a conducting pathway. What you create when you have an electric fence. You've essentially got these wires that you can see here. They are at a high voltage. And you've got this side down here connected into the ground, which is low voltage. And when your cow, who is standing on the ground, touches a wire, it provides a conducting pathway, admittedly quite a high resistance one, which is why the current isn't fatal to the cow, but it provides a conducting pathway and gets an electric shock. But until the cow touches the wire, there isn't a conducting pathway, and they'll just stay at high and low voltage. Okay, so that was a bit of an aside. Turn back to the question we're trying to answer. How does an electron know how much energy to give to a component? That's the big question we're trying to ask here. Let's come back to our traffic analogy. So, in terms of what's going on and how the electrons are a bit different to our traffic system, in our traffic system, we don't want all the cars to collide with each other. That would create massive traffic jams, lots of fatalities. That's not a good thing. So we are making the decision what this optimal speed is by doing computer models, doing some calculations and going, this is the correct speed. Okay, and then that produces the most efficient system we can. So the most efficient solution, it turns out by calculation, is when all of them are traveling at this same speed, and in this case it was 40 miles an hour. Electrons don't quite work like that. There's no system going away and calculating what the optimal speed is. What they do is that they collide with each other, transfer kinetic energy, and end up at this uniform speed throughout the wires or conductors in your circuit. So that it is slightly different. The reason being we don't really want to establish an equilibrium system by allowing all the cars to collide with each other. But you end up with the same result anyway. So that's what's going on with our electrons. I think an important question to ask ourselves now is, what determines the speed at which the electrons move? Because that's going to help us answer our question. In terms of constraints to us solving this problem, we want the speed to stay constant. So that means we need to keep the kinetic energy of our electrons the same throughout our wire. And in order to do that, we must therefore supply an equal amount of electrical potential energy as is transferred out by the components, so that we keep the energy of the electron the same in terms of kinetic energy. So in order to determine the speed at which electrons will move, we're going to have to construct a model of how resistive forces work in our circuit, because that's what's transferring energy out of our circuit. It's these resistive forces. And we're going to do it by using drag as an analogy or a model for that. So, a couple of things just to start off with. So, you might know that at high speeds, drag is proportional to speed squared. Whereas at low speeds, drag is actually pretty much proportional to speed. And we're going to be using this model down here. So this is going to be the model we're going to use in a circuit. And the reason for that is electrons actually move through the wires at pretty low speed. It's less than a millimeter per second. So that's what we call like the drift velocity of electrons. So we're going to use this low speed model. Now there are other factors to consider here. Electrons have sort of random motion around the wire as well, which is actually quite high speed, but we'll not dig into that too much at this stage. So what we're going to do is try and create a model by thinking of the resistance forces in a circuit like drag. So a few other things we're going to be drawing on. So work done by a force is determined by multiplying the force and the distance. And another thing we're going to be using is that if electrons are moving faster, they will experience a larger resistive force from the material they're moving in. And that shouldn't be a surprise to you, because if you think about a skydiver, the faster they're traveling, the bigger drag force gets. And it's the same in a circuit. So the faster an electron is moving through the circuit, the bigger this drag force, we're going to say, or resistive force is going to be. So it's the same kind of idea. So if we want to move electrons the same distance through a material, but faster, that's going to take more work. And that's going to be the key idea we're taking forward. So for electrons to go the same distance through a material, so say we're moving them through exactly the same conductor, but if we want to move them faster, that will take more work to happen. Okay, and that's an important idea. Okay. Another important idea we're going to integrate into circuits is that some materials have a larger intrinsic resistive force at the same speed than others do. So if you tried to move through treacle at 2 meters per second, it will require a lot more work than to move an object at 2 meters per second through air. And it's exactly the same for electrical conductors. Some require more work to move electrons through at the same speed, and maybe that's to do with the structure, the number of free electrons that they release into the conductor. There's loads of things, the temperature, but there's some things that will affect how much work it takes for an electron to move through at a fixed speed. So with particles, this is called viscosity, but we have different ideas with circuits. So what I want you to take out of this, essentially, when we think of a component as having higher resistance, many of the factors that make things higher resistance mean that to move an electron through the material at constant speed requires more work. Now, that's not true for all of them, so like cross-sectional area doesn't mean this, but things like length and resistivity and stuff are factors that link into this. So that's the idea. So that's a lot of ideas that I've scattered through there. Let's now pull them together and look at determining the speed at which electrons will end up moving. Here's the kind of the way I'd like you to think about a series circuit. So what I want you to think about is, like, let's say the air is there representing the wire. So something that's requires a fairly small amount of work to move through at a certain speed. Let's say a water is representing a small resistor. So it's harder than air to move through, but not as hard as treacle. So let's say large resistor. Okay, so this is kind of what we're looking at. So we've got a series circuit, and some components require less work than others to move our electron through at constant speed. So things that are going to place constraints on our solution to this problem, we have to obey conservation of energy, because we always do. So we can't do more work than the amount of energy we actually give them. And we want the electrons to drift through at constant speed, because all our computation models say that will be the most efficient system for moving electrons from one side to another. Okay, and that's what we're trying to achieve here. So in terms of building our mathematical model, let's call the speed at which electrons travel v. So at speed v, it takes an amount of work w to move a fixed distance through air. That's our starting point. And what we're going to say is it takes twice as much work to move an electron through water, and we're moving it the same distance at the same speed, and 5 times as much to move it through treacle. Again, at the same speed and the same distance. Okay, so the total work will be found by adding all of those two together. So in this case, it ends up being 10W. So that's a nice, simple example. Now, we could adapt this model for traveling different distances in each material, and that would be fine. And I'm going to show you how we might do that. So before we look at that, I just want to then link this into what our voltmeter is actually doing, because this is intrinsically linked to what we've just discussed. So a voltmeter tells you how much work it takes to move an electron through a certain part of the circuit at its current speed. So you can see the voltmeter across the air would tell you it takes W, across water it takes 2W, across treacle you see it's 5W there. So that's what a voltmeter is actually telling us in our circuit. It's telling us how much work it takes to move an electron through that section of the circuit. The EMF of your power supply is telling you the total amount of work available to do this work, if you like. So it's telling you the amount of energy you've input, and then we can then compare the two. So let's now think about how we're calculating what the speed is. And here's where it's important, when we spoke about earlier, the fact that resistive force is directly proportional to speed. So we can essentially create a mathematical model that looks like this one we can see here. So the resistive force is some constant times by the speed at which our electron is moving. And therefore we can generate an expression for the work done if we know the distance or the length of our conductor. So this is the work done to move through air. We've got some constant, the speed and the length of our conductor. So we said in our previous example, all of the conductors were the same length or the same distance, so it's going to be d for all of them. So if it takes twice as much work to go through water, what that must mean is this constant is twice as big. And you can see that in here. We've got 2k and we've got 5k. So this constant allows us to represent different materials which have a different intrinsic resistance to electrons moving through them. So now we've got an expression for the work in terms of this constant, the speed at which they're moving, and the length of them. Now we could make it more complicated at this stage by having different lengths of air and water and treacle, and that we could construct a different mathematical model, but it would just make it more complicated and unnecessarily so. But we could do that at this stage. Okay, so this is an expression for the work done to move our electron through the material, and you can see we've now introduced this speed term into it. So the work input, or the energy put into our circuit, is calculated using the charge of an electron and the EMF. And the reason this works is essentially the EMF tells you how much work is done per coulomb of charge. So then if we multiply that by the charge that an electron has, that tells us how much work we've done on our circuit using our power source. So that's what's going on here. So since the kinetic energy stays constant, we know that the input, essentially, which is what this is showing, so this is represented the energy input here, must be equal to the energy output. And again, we're assuming they're all the same length. The electron travels at a fixed speed through all of them, and this is the intrinsic resistance that air has to something moving through it, and then this is because we've got all 5 of those materials. So essentially, we can determine the speed at which electrons will move if we know the lengths of the conductors, if we know the EMF we've supplied, and we know how hard it is to move through each of the materials, this K. That's what, by thinking about our electrons in this sort of traffic air resistance type model, predicts. So I think what would be useful to see here as a checkpoint is, does this actually agree with what our electrical equations tell us about the speed at which an electron moves? Here are some equations that we have when we're modelling circuits. If you're not doing sort of A-levels or pre-U yet, you will not have met some of these equations. But essentially what we've got is we've got an equation, so this equation links the speed at which electrons move and the current. So this N is what we call the free electron density. Here we've got the cross-sectional area. Here we've got the charge of an electron, the 1.6 times 10 to the minus 19 we met earlier. And here we have what we call the drift velocity. In our next equation, the L is like the length, air is the cross section, R is the resistance. The one you may or may not have met before is something called resistivity, a measure of like a material's intrinsic resistance to passing a current through. And the other ones should be fairly common there. So what we're going to do is see whether our model matches up with the equations that have been found experimentally from measuring circuits. So, first thing I'm going to do is rearrange the first equation to make the drift velocity the subject. Then in place of current, I'm going to put potential difference divided by resistance. And then I'm going to put in place of resistance the resistivity times length over cross-sectional area. And you'll notice the cross-sectional area cancels out. And what that tells us is the cross-sectional area plays no part in determining how fast electrons move. And you'll remember that in our model, there wasn't a cross-sectional area in there either. So that kind of works. So that's good. So what we can do is we can simplify it to get a model that looks like this. Now, if we compare that to our model, and again, I'll rearrange it to make the drift velocity or the velocity of electron the subject, we can see a lot of good things in here. We can see we've got a potential difference in both of them. We have EMF actually in ours, but essentially it's a potential difference or increasing the energy. We've got a distance on the bottom line, and we see we've got length on the bottom line, so that looks good. So a longer conductor essentially is going to make the speed go down because it takes more work to move through a longer conductor. That makes sense. And we've got some sort of properties of the conductor and the electrons, and we can see that that matches up with this equation over here. Now you'll note that the charge of electrons seems to be in the wrong place. I'm not going to dig into that too much because we haven't really explained what resistivity and free electron density are either, but essentially we can explain the reasons for there being a different position there. So our model looks good. It predicts the same things that the experimentally determined model does on the left-hand side. Okay. Let's return back to the question we started with. How does an electron know how much energy to give to a component? Briefly summarize some key things we've seen. A voltmeter is measuring how much work an electron must do to move through a component. The different voltmeter readings reflect that it takes different amounts of work to move through the different components in your circuit. And the electrons will determine that amount of work by essentially arriving at a fixed speed which they'll move through the circuit, and that speed will allow them to both obey conservation of energy and maintain a constant speed as they move throughout the circuit. These are our key ideas in terms of that, and it's this constraint at the bottom that determines how fast they move, and how fast they move determines how much work they will do to move through a given component, which is what our voltmeter is reading. So actually the electrons aren't making a decision. The voltmeter is just telling you how much work it takes to move through a given component. So I would like to finish by drawing an analogy to a completely different system to help you get a feel for, again, how this is working in the same principles in operation. So with a bike, the work is done by the rider of the bike initially to increase the kinetic energy, yes, but once they're riding along, they are maintaining a fixed kinetic energy. And that's the point I want to compare it to. So not the acceleration phase, when they're riding along at constant speed. So the rider is playing the role of an EMF source. They're putting energy into the system, but the kinetic energy of the system is staying the same. And the reason it's staying the same is because different parts that are in contact with the wheel will be applying friction to the wheel, and that will be transferring any energy input into heat. And if the friction is different sizes in different places, that will generate different amounts of heat. So the system is not deciding at each point, oh, here I will transfer 2 joules of energy, here I will transfer 4. What's happening is the amount of heat is determined by the speed at which the wheel is moving, and the speed is determined by applying conservation of energy. So it's exactly the same idea.